Hello AP Physics students, this is Dr. Brinzy here, and this is a video on lesson 9.6, and in this lesson we're going to be talking about what's called driven oscillations. In this lesson our objective is that we're going to be able to qualitatively describe what happens to an oscillator when it is driven by a sinusoidal force at different frequencies. And then we're going to also be able to describe the cause of resonance in a driven oscillator. And we need to know actually what that thing resonance is. And then calculate the frequency at which it occurs. So in lesson 9.5 we learned about a damped oscillator. And a damped oscillator consists of a mass on a spring. So here's our spring, here's our mass. But alongside that is a piston that is either run or is a rod that either goes into a bit of compressed air, which would be called a pneumatic damper. Or it might go into a viscous liquid, which we talked about, and that would be a hydraulic damper. And what we're going to do today is we're going to actually drive this thing. In other words, we're going to actually add another force. And we're going to consider this force to be a sinusoidal force. So somebody is applying a force somehow that varies over time by this function right here. Okay. I just noticed that one of the things I did not do is on my little diagram right here. You're probably wondering what that symbol is, or you might have forgotten what that is. That's actually from a previous year that I used a slide. Last year I used capital omegas, and this year I'm using small omegas. So really this thing should be the same as that. Okay. Alright, so we have somebody basically pulling this thing back and forth with a variable amount of force, and that force varies as sine of omega d times t. And this omega d is actually something that it's not a property of the system itself. It's something that somebody determines externally. So somebody could choose to shake it or to move it back and forth at that angular frequency, but it doesn't depend on anything about the system itself. It's just a selected frequency that one is driving this thing with. Okay. Now some interesting things happen when you actually drive an underdamped oscillator with a sinusoidal force. One of the things is that this that entire system, its displacement matches the driving frequency. So if I go back here, back to my diagram here, so if I were to decide, if I made a decision to like drive this at 5 radians per second, then what would happen is that this entire thing would oscillate at 5 radians per second. So it would match whatever is whatever that driving force is, that driving frequency is, excuse me. Okay. So one interesting thing is that that frequency that it moves at doesn't depend on the stiffness of the spring, the strength of the damper, or the mass at the end of the spring. And that's not something that we're used to, because we're used to saying, oh, the angular frequency is omega equals k over m, or root k over m, excuse me. And those are properties of the spring and the mass. Or yesterday we learned that this damping force, or damping constant B, also has an effect on the frequency at which that system will oscillate. But now that we're driving it with an external force that has a frequency omega d, all of that goes out the window, which is kind of an interesting fact. So the frequency is always determined by what the driving frequency is. Now, even though that's the case for frequency, that's not the case for amplitude. A driven oscillator has an amplitude that changes depending on several things about the system. First of all, it depends on the maximum amount of force that one applies to the system. It also depends on the properties of the system, like the spring constant, the mass, the geez, I just had a brain fart there. The damping coefficient, there we go. And it also depends on the driving frequency that we use. And what's interesting is that if you plot this as a function of your driving frequency, it has a shape that looks like this on the left. So it starts off at some value, but then when you hit a certain point, that amplitude actually increases greatly and then decreases again, and it looks like it decays here. So if we select the right driving frequency, omega d, then it looks like we can cause this amplitude to actually increase by a large amount. So there's a certain driving frequency that causes the amplitude to increase by a huge amount, much more than what we are driving it with. And this phenomenon that we observe in driven oscillations is what's called resonance. It turns out that this resonance occurs if we decide to drive this system at its natural undamped frequency. So if the driving frequency, if we decide to set that driving force so that it's operating at the same frequency as the square root of k over m, then we can increase this amplitude by a huge factor. And that phenomenon is called resonance. So this amplitude A, when you decide to set the driving frequency equal to the square root of k over m, then the amplitude actually becomes this much more simple form where you have the maximum force divided by the damping constant times the driving frequency. Now, one thing I want to say about that before I get to my second point here. So where does this come from? Where does this simple thing come from when what we had before was such a complicated function? And I'm going to back up to that more complicated function here. So this thing becomes that much more simple form. It just becomes f max over b times omega d. Well, why does that happen when omega d equals the square root of k over m? Well, what happens is that this term becomes 0 when we are at the resonance frequency. So when omega d is equal to the square root of k over m, this term disappears. So that causes this term to become a minimum value, which causes the amplitude to become a maximum value. So that's what's happening when we drive this thing at its resonance frequency, or at its natural frequency, the square root of k over m. Okay. Now, if you look at this amplitude, when this value of b is small, what that causes is this amplitude to increase. So the smaller the value of b, the larger the amplitude we're going to have. So a lower damping coefficient, B, causes a stronger resonance. And on the other hand, a higher value of B causes a lower or a weaker resonance. Okay, you can actually see that on this plot because what's plotted here is the resonance at different values of B. So this is B is equal to 0.2 times a constant value, and then if you double it, the resonance actually gets smaller. And if you double it again, the resonance gets even smaller. So we're not increasing the amplitude very much above what it would have normally had at other frequencies. So changing this value of B modifies or changes the amplitude. Lower damping coefficient causes a stronger resonance. Where might you actually run into something like this in real life? Well, there's several things that have resonances, and I'll give you a couple of examples here. So, one example is an opera singer who can actually break a crystal wine glass by just using her voice. And what she needs to do is she needs to find the right pitch, and the right pitch corresponds to the right frequency that she is emitting sound waves at, and when she finds that right frequency, that causes the wine glass to go into a resonance, so it fluctuates, it vibrates at a very large amplitude, and eventually the crystal can't handle that, and it will shatter. So that's an example of resonance causing something to break apart. Another example you might have actually run into at some point is a very famous bridge disaster called the Tacoma Narrows Bridge. So this bridge failed not too long after World War II, if I remember right. It was about 1949 or so. And what happened is people observed this thing twisting back and forth on a windy day across the Narrows, and this twisting motion just kept on getting bigger and bigger and bigger until finally the bridge ended up collapsing. Now, experts disagree as to how resonance played a part in the destruction of the bridge, but I think it did play a role. Now, the reason that some people say, well, I'm not sure that this is a good example of resonance because, after all, the wind wasn't pulsing, it wasn't going sinusoidally, it was a steady wind, so there's no, sinusoidal driving force. But on the other hand, if you get this thing starting to move, then you have wind pushing on it when it's twisted, and so that wind can act as something that is driving it with a certain frequency because the bridge is fluctuating a certain frequency. Anyway, so that's kind of like a debate that rages on, but I think it's a good example of resonance because that amplitude of that twisting motion gets much, much larger at a certain frequency until the bridge can't stand it anymore and it collapses. Okay, there's a couple of real-life examples, and those aren't the only real-life examples, but those are a couple of famous ones. Let me give you an example now from the homework set that you might encounter. So let's go to that here. So let's read through this here first, because there's a lot of text involved in some very new language that we learned we have to figure out here. So we have a driving force. It's applied to a damped harmonic oscillator. And this oscillator has a force constant K, so it's a spring constant. And it has a mass M. And then it says here, if the damping constant has a value B1, then the amplitude is A1 when the driving angular frequency equals the square root of K over M. Now, when the driving angular frequency equals the square root of K over M, like it says here, Let me see if I can highlight that. When the driving angular frequency equals the square root of k over m, that tells me right away that we're talking about resonance here. Because that's where omega d is equal to square root of k over m. Okay, so when this thing is at resonance, then its amplitude is A1. Whoops. Sorry about that. Oh, I'm starting to write some givens that I didn't want to write yet, so let me back that up. So in terms of A1, what is the amplitude of, if the damping constant is changed to a different value of 2B1 instead of B1? Okay, so we have a kind of like a before and an after situation, and I'm kind of like being asked, okay, when the damping constant is changed to this value right here, what is going to be my new amplitude? Okay. So I'm going to take some notes about the driver here because some of those pieces of information are important. And so I know that omega d equals the square root of k over m, which immediately reminds me, oh yeah, that's resonance, right? So this harmonic oscillator is going to be in resonance. There we go, resonance. And then the system, it tells me that it has a mass m, it has a spring constant k, it has a damping constant B1, and when all of those things exist, then we have some sort of amplitude A1 at resonance. Let's not forget that this is in resonance. And I'm being asked, okay, so if you change from B1 to 2B1, what is this new amplitude going to be at resonance? Okay. So let's think about, okay, what do we know about amplitude when something is at resonance? At resonance, we know that omega d is equal to the square root of k over m. Yep, we knew that. We wrote that down already. We also know that the amplitude is going to be F max divided by B times omega d, which is the driving frequency. I wasn't given any information in the problem about F max. But I am thinking that maybe it will drop out. Maybe it won't matter. So we're going to try to continue this problem and see if that F max somehow drops out. Oh, and by the way, this is A1, so I better put A1 right there. Okay, so that's a situation when that I started off with. So this is when we have spring constant K, mass M, and B1 right there. Oh, wait a minute. Hold on here a minute. Maybe I rewrote this down. Ah, there we go. Okay, so A1, the first situation is A1 is equal to F max over B1 times the square root of K over M. Okay, so I just plugged in what omega d would be. Now I have a new situation. Let's call that A2. And that new amplitude should be F max divided by, now instead of B1, I want 2B1. And then I'm going to have the same driving frequency because it's still at resonance. So that driving frequency is going to be square root of k over m. And now what I need to do is just find a way to get this entire thing, this thing right here, to get that to equal some constant times this thing right here. And I notice that the only difference between these two things here is that there's a 2 at the bottom, so I can factor out that 2. And since it's in the denominator, I'm actually going to have 1/2 times F max over B1 times root k over m. This entire thing is equal to that. So I can replace this with 1/2 times A1. Okay, so if I double the spring or the damping constant B, I will get half of the resonance amplitude that I had originally. Alright, so that's how you might actually need to deal with a driven harmonic oscillator, dealing with amplitudes and frequencies at resonance. And today's problem set is going to be dealing with a lot of those types of problems, dealing with amplitude and angular frequency at resonance. Alright, hope you find this helpful, and look forward to seeing you soon. Bye.